Okay, thank you to be here also today for the lecture. Let me start with another example in which an augmentation generates a nonlinearity, or better to say more than one nonlinearity, and then we need an extension, or better to say an extended Kalman filter. Do you remember, we have seen, in any case, we have seen the extension in case of the motor, do you remember, which we want to estimate the resistance. Tamo, you were there when I told you about the estimation of the resistance in the context of the motor. You remember this, Tamo? To estimate the resistance in the context of the motor, with generated a nonlinearity because we have the resistance which multiply the current, and where is the nonlinearity? It's exactly the resistance multiply the current in the moment in the moment where I would like to say I consider R, the resistance, as a state. But let me repeat everything now, a more complex, I don't want to say more complex, but in a system with two extended parameters, and then we will repeat the concept of the nonlinearity. And this is a good introduction for the concept related to the observability, because the question is, how many parameters can I estimate? This is a little bit the question of today. Okay, let me consider, we are starting exactly now. Let me consider this example. It's a shame for the not engineer, it's a little bit strange, but as we discussed before, when we have a model, you remember in our bacteriological model, when we have the model, then basically a drone, dynamic bacteriological system, an economical system, wouldn't have many differences. Here is similar, the concept. This is also a very important concept. Desiccator system using radio frequency. Let me tell you about this project. This is a relative old project, real project. In fact, we can see here a nice picture. I don't know if it's nice, but just to show you that some concepts can be applied in real applications, in the real world. What we can do here. Yeah. Let me tell you about the system here. We can see here two electrodes. We named cold and warm electrodes. Why that? Because inside these two electrodes, I can put an object to be desiccated. You know the word desiccation? Yeah. German, I think, is to be trocken. We have an element which is weight, humid, and we want to eliminate this humidity. Could be used in some wall, could be used in some particular objects. This means the idea is in a temperature control. Using a capacitor, for the engineer is quite clear, and applying voltage on these two electrodes. We have a current inside, and this current generates a temperature, and the temperature is able to desiccate, to eliminate the humidity. I don't want to insist on this part here, but in any case, this part here is there to adapt the impedance. That for the engineer makes sense. For not engineer is not relevant. For not engineer is just to think that we can generate an equivalent, I would like to say, circuit which describes somehow electrically this system here, which can be seen as a capacitor. Inside the capacitor, we have an object to be desiccated, and this other box here, or the boxes, is there to adapt with this matchbox to adapt electrically the radio frequency generator with the load, which is represented by the capacitor and what we have inside these two plates of the capacitor. The idea is using an input, a radio frequency input. If you're not engineer, forget this. In a signal, we generate a voltage, but with particular frequency to obtain the temperature between this, let me say, element here and this element here. And if you look here inside, we have many capacitance, because I can think to desiccate also particular elements, for instance, in alimentary industry, tobacco, to desiccate the tobacco. You can disseminate here your elements, and then of course we can think about that with this voltage we generate temperature. At this moment, the model which I am considering here is without temperature, because otherwise for the lecture a little bit more complicated, but the temperature is in a function of the current. I mean, look, we have the capacitance here, or capacitor, better to say. This R here could be a model of the object to be desiccated. This L here represents this box, which is there in order to adapt the impedance between the radio frequency generator and the load. Forget this technical aspect. This is the circuit which we want to analyze. About the Kirchhoff law, about the circuit, I already told you a little bit considering the motor. Here is a little bit more complicated if you want with respect to the motor, but I don't want to say more complicated because the motor is also complicated because we have a rotating part. Here we don't have mechanical part. But let me go ahead. Assuming that we are good in math, assuming that we are good in electrotechnics, I can show you, I don't have time to show you, but we can write the Kirchhoff laws for this system here. And after, we have seen in the motor, no? After the calculations, we can obtain a model which looks like something like that. It's not totally different with respect to the electrical motor. Of course, it's another system we can recognize also from the structure of the matrices. But in any case, we had, do you remember in the motor, we had the two states, current and velocity. Here we have two states, current I1 and U2, the voltage on the capacitor. Because if you remember the concept of the state represents or reflects the energy. Which kind of energy we have here? As in the motor, the magnetic energy, electromagnetic energy. In the motor, we didn't have the capacitance, but here we have a capacitance, or the capacitor. This means we can think that the energy which plays a role here is the electrostatic energy. Therefore, two states. Believe me now, we can build the model as we did in the tail for the motor. Of course, in the motor, we use the Kirchhoff and we use the Newton law. Here is enough to use both Kirchhoff laws, node laws and circuit law, excuse me. Yeah, anyway, believe me that we have this kind of model. Now, look here. It's extremely important to understand what I'm trying to do. Do you remember in the case of the motor when one goal was to estimate the resistance? And if you remember, we have the current at the state, omega, the velocity of the state, and then the resistance. Here, I pretend something more. I pretend to estimate the resistance and the capacitance. This means I will extend the system with respect to the resistance. I will extend the system with respect to the capacitance. This means we don't have just 3 states as in the motor, but we have 4 states. But the concept is the same. If I don't have an idea about the model of the resistance, about the model of the capacitance, we have seen from the beginning, I can consider the derivative of the resistance and the derivative of the capacitance equals 0. We can recognize here how many zeros we have. In fact, this equation here, the derivative of R, is equal to 0. The derivative of the capacitance is equal to 0. But we are in the presence of a nonlinear system. Why that? Yeah, because we can see, even though I didn't emphasize here, that R, C are function of the time because they are considered as state, augmented states. This time, not only the resistance, but also the capacitance. It's a little bit more complicated than last time, but the idea is always the same. Considering a Gaussian variable, R and C, or the two Gaussian variables, inside, let me say, the linear model. This means the linear model becomes, we can say so, a nonlinear one, because here we have the product, not only the product, is 1 divided. Here we have is 1 divided, and not only, we multiply, we can see here 1 divided C of t, 1 divided C of t by I1. This means I1 is divided by C of t. This means, in any case, we are in the presence of nonlinear system. And also here, the nonlinearity is quite complex here. This element here is multiplied by U2. This means U2 divided R of C, R of t and C of t. We can understand very well that we are in the presence of a nonlinear system because of this division, because of this multiplication. Yeah. But it's not as new with respect to the extension, augmentation, which implies an extension in the case of the linear motor, of the model which we analyzed last time. Now, do you recognize? This is the case. You know exactly what I intend with this notation for the linear case, but we are not in the linear case. We are not in the linear case. This means if I do the discretization, the same discretization, the same method which we are using until now, Forward-Euler, but not necessarily this. We can use also different methods. I don't have time in this course to specify or to go in depth with different methods. Let me go ahead with this is the standard one. But of course, we have a differences between. If I apply this method, I will obtain, in case not augmented, this means not extended, this one. We have seen for the model, this is just an example in order to recall. You remember, TS, simple time, appear everywhere. This factor 1 is there because we have an identity matrix. Now, we are in the presence of a nonlinear system. This means we have the equation A, which states our prediction. We are in the equation A already in the Kalman structure. You remember, I emphasize a lot, no? Here, hat minus k hat without minus k minus 1, the concept of the recursivity. Do you remember this? Now, if I consider the Forward-Euler of my nonlinear structure, we will obtain this prediction here. How I can do that? Yeah, it's not so difficult. Even though here, of course, yeah, we can consider so. But sometimes in some books we have hat also here on I, on U2, on C, but this is just in a formal. Let me say, is in formal. Notation. I can realize this just considering. Let me see if I have here. No, I don't have. This expression which came from this if I discretize. I didn't do, but I will show you with MATLAB how we can do. Applying to this matrix here, if you want, to this matrix here. This is the matrices. This criterion here. Believe me, we have this expression here. Or you can, if you don't like this, yeah, we can do considering the nonlinear, the expression of nonlinear system more properly without using this formalism here. But in any case, we can also use this formalism here. I will come back using MATLAB Simulink. We need the Jacobian matrix. It's exactly what we did in the case of the linear motor, because basically we needed the Jacobian calculation. The Jacobian calculation, I repeat it here, which is the matrix of the partial derivative of all states, including the augmented. And if I apply this definition to this system here, because we can see here, no? Yeah, the derivative of the I1 with respect to the I1, the derivative of I1 with respect to the U2, and so on. But I1 is this line here. It's not clear visible, but you can see here, I1 of k is equal to this expression. And we can see that 1 minus TS 0, 0 can be very easy justified, because if I do the derivative of this expression here with respect to I1, I have 1. If I do the derivative of this expression with respect to U2, I have TS divided L minus TS divided L. Believe me, as we did for the motor, we can do also here. It is a little bit more complicated. In particular, the second line is complicated because if you look at the equation, is a little bit more complicated, but it's an exercise of the derivative. If you are not good in the math, we can use a toolbox of MATLAB to do this calculation. I will show you. The Jacobian of this line here, let me say so, the Jacobian of this line here is extremely easy. I hope that I share. Yeah. Stop me if I didn't share, because sometimes I forget. Yeah. Because we have just one at this position, because at this position we have the derivative of R with respect to the derivative of R of k minus 1. The derivative of R of k with respect to the derivative of R of k minus 1. Exactly as we had in the case of the motor. And here we have only 1 here, because if you look at this equation here, we have just C of k minus 1. Yeah, this is the Jacobian. Now we can apply the Kalman filter. If you remember the lecture in which I introduced the nonlinear form of a Kalman filter, which basically is a linearization of the equation B in case the nonlinearity is just in the state. Do you remember? I insisted on this. We can see here, instead of the matrix A, I have the matrix J, which represent the Jacobian, the derivative. Let me say, do you remember I told you about the Taylor approximation and so on? Very important is also this element here, which is also present in the linear case, because, of course, in this case is probably more important, I would like to say, because here, in this Q, I summarize what I approximate with Taylor. And then I can apply. H, in our case, equals H not capitalized. H capitalized equals H not capitalized because we don't have nonlinearity in the output. Basically, equation C, D, and E does not change. Let me now show you the implementation. But for the implementation, I would like to open MATLAB so we can see also the results. Let me go out here. Here is I copied basically from the file of MATLAB. Let me open MATLAB. Let me see. I am opening MATLAB. I hope this is working. Yeah. I need a little bit time. Okay. Let me share so you can see. Basically, what I am telling you today is exactly what I already told you in the case of now where is I don't see MATLAB. Okay, now what I already told you in the case where is MATLAB? Ah, here of the motor, but we have a parameter more. Come on, I don't know if it's clear now. What is difficult? The Jacobian, the model? No, it's okay. No, I will repeat now a little bit. Exactly. Let me see where I have to go now. One second. This is the lecture. I am looking for found it. Okay, let me open this file. This is the file of the data. L, C, R, and TS. Let me run. Ah, stupid. Let me run the data. Yeah. Now let me open the file. Let me open which one? I think you have voltage and current. Let me consider one of both. Let me consider one of both. You can see also in your case, you have, I think, voltage measured and current measured, right? To simulate in my study, right? We can open one of them. For instance, voltage measure. 1 second, I need time. And then we discuss the results together with the implementation, of course. Okay, look, let me share Simulink. Look, here we have the system. This means here inside, with this expression here, or with this representation here, I have the continuous system, which I introduce very quickly at the beginning, but reflects more or less the method, at least, to obtain this model here, which represent the real system, what we have seen in the DC drive. Of course, yes, not a DC drive, is an RLC circuit. In fact, we can see, no? But in any case, is the, let me say, representation of what? Let me show you in the lecture so I can be a little bit more concrete. This system here, X system, and Y, considering both outputs. I represented somehow the model, because this is the real system, or at least, and the model, of course, of the real system. At the end, what we did in the project, this is very important. The real system is this one. Not only this one. If you want to be precise, the real system is in between these places here. Anyway, let me look here. This could be considered the real system. And practically, in the application, what we did is we replaced this with the real system, and we give voltage to the CK, and with our microcontroller, with a computer, we measure the input, U2. No, this is U1, no? U1. We measure one output, could be the current, could be the voltage. In our application, we are considering the voltage. Of course, the sensor may mistakes. Do you remember the concept of the Kalman filter? And then we have the Kalman filter here inside in the microcontroller, in the computer, to monitor what? In this example, to monitor the voltage. In the more practical example, in the application, we considered also this application, exactly this, but then we implemented also a more complex model in which we have the temperature. But also this model here, or that this Kalman filter based on the voltage, worked quite good, no? Because we can build a mathematical model directly between the current and the temperature. But anyway, just to understand practically that here we have the real system. In this case, we are measuring, we can see here, the voltage. Therefore, I considered the file in which we have voltage measured. And here inside, we have our Kalman filter. Let me show the Kalman filter here inside. The Kalman filter here inside now is not an interpreted Kalman filter, let me say an interpreted file, but an embedded file. In fact, you can see if I click, I have exactly the M file. More. You remember at the beginning, in order to understand a little bit better the concept of the Kalman filter, I considered here a different structure, this interpreted file, which we have in a complex max, which coming back, in which I put back do you remember the covariance matrix, the states, and here we have 1 divided z as initial value for the initial state, for the covariance matrix. Now everything is here inside. I would like to say this method, this embedded is used in practical application because we can flesh out directly everything, or almost everything is the microcontroller. With the embedded, we have to transform. Didactically, I would like to say what we have seen until now, it is better because we can understand a little bit more, I don't want to say better, but the concept of the Kalman filter. But in any case, now I try to explain the difference here in between. But the difference is easy to understand now, I think. 1 divided z here, because in the forward Euler, we have to delay the input. Look, the function of x, which is a vector, we will see which one. Sample time. We can also put the sample time as an argument, but it is, let me go here. Also, L, also everything which we have here can be also defined here with a comma, but let me go here in this form that is probably a little bit more direct. I don't want to be heavy with the different notation or variations and so on. Very important, the parameter must be given to the to this function, I would like to say. Do you remember in the interpreted, we use the function global. If you look what we have seen until now, basically global allows to read variables or parameters from everywhere, let me say. Please pay attention here. Is the difference. One difference is here, persistent. Persistent is an interesting comment. After persistent, I can define variables which can be used recursively. Therefore, the word persistent, remain with this variable, reuse this value persistently. The other difference is here. If x alt is empty, then put the initial value. This means at the beginning, this if here is active, and then no more. This replaces, this if here replaces 1 divided z. Do you remember 1 divided z in the interpreted? At this moment, you can forget the interpreted. The interpreted I use didactically, in my opinion, to understand better. Basically, these 3 values can be given, interpreted in 1 divided z. In 4 values, excuse me, 4 values. Now we have initial value of the current, initial value of U2, voltage of the capacitance, initial value of R, initial value of C. I assume that I don't know this value. In fact, if you look their difference with the true value, I can speak about the true value. The true value can be seen in the M file. Let me show you the M file. Really, this is the true value. In practical application, well, God knows the true value. But here we know. R is 1, and we put 5, right? C is 3, 10 up to minus 3, and we put 5. Oh, I don't remember. Let me look. This is the true values. Yeah. Instead of 1, I put 5. Instead of 3, right? I put 5. Correct, no? I remember well. R was 1, I put 5. 5 times more. And extremely large error. 5 times more. And here again, it was 3, 10 minus 3, something like that. I already forgot. It was 3, no? The capacitance. The true values in the M file. I put almost twice, big errors. Current and U2, I don't know. We have to look in the Simulink. We can see, and then Simulink directly now. I put 0, 0, and here we have for U2 0. I don't share, but believe me, and for the current 0, this makes sense because I considering that I am starting with the observer exactly when I start with the input. Of course, the capacitance and the inductance not necessarily at the initial condition 0, but I can suppose it's almost 0.
The two currents from the scope current 1 and current 2 are the Kalman gains.
The Kalman gain, let me see. Good question. It seems now I will look because we have a 4 Kalman gain, K11, K12, and this could be K, let me say 3, K4. We have a 4 Kalman gain in column structure. Please pay attention. Question me.
For current, for voltage, for R, and for C.
Yeah, perfect. We have just one column because we have just one input. When we have more than one input, I don't know if in this course I have probably yes, I have something like that, but a little bit more complicated because the column of the Kalman gain matrix, the number of the column of the Kalman gain matrix equals the number of inputs. A little bit more complicated. If I have time, I will tell you also in the course. Otherwise, we can look on projects. Yeah, because I will act on all variables using my Kalman structure. Yeah, I didn't put let me say KN3, KN4 because in this course I don't have time to analyze exactly the Kalman. It could be that I will tell you something. These elements here are not relevant, at least in this Kalman filter structure, for the calculations for the algorithm. It's just there to the back.
Kalman filter gets voltage as the input in this point.
The voltage, yeah. This here is the voltage, right? We can see here is the sinusoidal signal, as in the real case. Yeah. Thank you for this question. Yeah, and we can see that we have noise in the input and noise in the measurement. That is a little bit strange, which I put the same noise. You can put the different noise. Different noise means you have to go here inside and to change the seed, a different seed. But anyway, you can test with different noises because not necessarily the same. But in the theory of the Kalman filter, we have to assume that this noise is Gaussian. You remember this? If it's not Gaussian, we have to speak about another kind of Kalman filter. Theoretically, it's not equals. It's not equal, of course. But I put here just to go a little bit faster.
Why is the estimated values from Kalman filter different to the yield of the system if it has the same input?
Excuse me, I wasn't thinking again.
If the Kalman filter gets the same inputs with the same noise as the system, why does the estimated states are different than the real states?
I mean, you ask, basically you want to test with different noises.
and at the moment, Karman filter and the electrical system gets the same input.
Yeah, here.
Right? Yeah.
This is always so. This is always so. Now, the limitation, but it's not a big limitation. If you want, I can't. Is that I assume that they have the same noise. This cannot be. Here, if I change the seed, not the same seed, now we have a different noise. In our Kalman filter, means our, this is the meaning of our. In our course, I'm considering Gaussian noise. If the noise is not Gaussian, we are speaking about a different Kalman filter, which is, we have to, in the literature, if you look now in the literature, Kalman filter in the presence of not Gaussian noise literature. We don't have time. Yes, it's very much. Basically, this is the most important because you know that in the natural phenomenology, the Gaussian is the most important because it's the natural error, the natural noise, and so on. Moreover, also different distribution if we repeat tens to Gaussian. Anyway, I'm not expert about that. No? But anyway, this is the most important aspect, which can be used, approximated also processes with different distribution of noise. Let me go a little bit in depth on the structure here, and then we will discuss the results. And then I would like to tell you about how many parameters can I estimate. You remember in the model it was one parameter R. Now today we have two parameters. I have the system of the second order, both cases. I measure in both cases one output, one input and one output. Question is, it is possible to estimate also parameter L, and then I would like to start to answer the question at the end of the discussion of the simulation. I have to come back a little bit on the concept of observability, nonlinear observability. But of course, I don't have time today to complete this, but I will start. Look at this. As I already discussed this, no? Again, I can do the same for parameter P. Do you remember our feedback in the Kalman filter was for the state vector and from the P? Here we have inside this quantity of the initial value. The rest of the Kalman filter is basically the same. Here, I change just the name of my input, of my output. Here, I think it's an error because in this file, I think we measure the voltage. Let me see. If it's an error, I would like to correct. The second variable was the voltage, right? Or the current, I don't remember. Yeah, this means an error just in the comment. Né? I am measuring the second state. I don't know. Let me check because I'm not sure which file I am using. Is this written voltage measured? Let me see. Yeah. Yeah, it's no voltage. This means it's just the error in the comment here. This means I have to write U2. Yeah, it's exactly this. Here we have a U2 as the state to be estimated. Here we have a U2 measured. Do you remember I emphasized this difference inside the Kalman filter? We have this and U2 measured. It was just wrong, the comment. And here we have a U2 estimated, which came from the previous, I show you why, from the previous estimation, or the correction if you want, as this one. Thanks to the persistent, I show you in 1 second. I measure U2, therefore here was an error here. No? What about this? This is the model. If you're not clear where the model comes from, I can do the calculations for you. But I did for the motor, if you remember. It's not so difficult here to calculate this. More difficult is the Jacobian, but also this, if you don't like to do the derivative, you can use the command diff. Please look at help diff. Also, I think help Jacobian. If you go in MATLAB, help Jacobian, you can apply Jacobian to this X star. I don't remember. I have to look. Should be something like that. Should be something like that. Let me write as in a comment. Please check at home. I don't know if it exists, but I think so. Something like that. Tamo, if you look for me, should be something like that. I don't remember exactly. This command here probably capitalized, of course, without should generate exactly this. Look for help Jacobian. I don't remember if it's written with the. I can look. Because of course, otherwise I have to do by hands. You understand what I intend? The full matrix. Now, this is not extremely complicated, but nevertheless, the calculations can generate mistakes. No, I'm not good in math. Let me show you if this is exactly what I intended. Help Jacobian. I wrote capitalize. Yeah, better capitalize. No, not found. Strange. Not found. Did you find Tamo something? Otherwise, you can build with diff. Look for Jacobian. Huh? Let me see if I find something. Look for Jacobian.
See.
Ist
mit C geschrieben, Schwester.
Capitalize? Ja. Exist. I don't know if it's this one. It could be. Look a little bit at home. Otherwise, you can. in my opinion, was something like that, but I'm not sure. Huh? Basically, I would like to do something like that. Eh? but the argument is the function, and then the element, the variable, no? Should be something like that. But I'm not sure. Please check. I write for you. Please check. Okay. Should be exactly what we did by hand. The rest is the Kalman filter, which you already know. Because basically the extension is, at least in this case, in which the nonlinearities are in the state, exactly the Taylor approximation of the a priori error covariance matrix. The rest is exactly the same. What I would like to emphasize here is in the technical aspects. Look here. Look at these two lines, 56 and 57. I pass, or I save the value pxn or xn, basically what I calculated for the a posteriori error covariance, what I calculated for the estimated state, for the next one. This is the concept of is connecting with the persistent. Persistent. Tamo, you know probably, you already knew this. Persistent and so on. Huh? Basically, at the beginning, I define P alt and X alt as persistent. This is close this concept of the persistence here, because in the file of last time, I did the recursivity outside using this max, using this line that is go out and go again in input. Here is more complicated to be understood, but more practical because I can flesh out directly this software in the microcontroller. Basically, I say to the system, use for the next step persistently what I calculate now. Let me run. What is important here? Of course, it's important to estimate everything. Current, voltage, R, and C. Question.
Can you go on this go with compare currents?
Second. Current you want to see?
Yeah.
Yeah, current is very important because we don't measure the current. Also, voltage is important because the estimated voltage is better, at least theoretically, with respect to the measured. Let me show you this. I hope it works. Does it work? Let me see. Ah, yeah, you're right. I didn't see. I hope it's working. Because it sometimes I change something, then was the discussion, then I forget to come back. But I have a file which is working. Now we will see. Yeah, we can see that is not very well tuned. Let me share at home. Could be improved. I leave this exercise at home. Yeah, we can see that is not very well tuned, but the task is extremely hard because we have 5 times the initial error in the resistance, at almost twice for the capacitance.
Beginning.
At the beginning.
Yeah.
This means, yeah, this is a little bit the reason. We will see that at this time, this means after 10 seconds, we have the right estimation of R and C. This is a little bit the reason. Now, how we can improve? PSO try, I can send you an interesting Kalman filter on the estimation of insulin and different hormones with tuning of matrix Q, P initial with the PSO. They try to do at the beginning some runs, and then put the initial value so we can reduce this. But the problem of the tuning the Kalman filter is the problem of the Kalman filter. I met once Professor Kalman in the conference. I told you already. A professor asked him when the Kalman filter does not work, because it's applied everywhere, really, almost everywhere, with different variation. We will see also in the rest of the lecture. I will hold the lecture until middle of February to recover the lecture which we lost, more or less. It's really applied with different variations. And Kalman answered that Kalman filter cannot work. And then we clarify, because cannot be tuned exactly. But of course, we can arrange with neural networks, with PSO, to, for instance, here, to reduce this time. But we cannot reduce to zero, because God knows the initial value. Or the parameter of Q and RW, no? RW, the matrices to tune, and also P0, no? Do you remember? Let me answer better this question of Tamo. Look in here. R and C. Let's look at R here. You can see that more or less at time 10, more or less, no, we have the right estimation. You can see here now. Everybody can see what happens. No? The error is extremely large, 5 times. Kalman filter needs time to understand. At this time, I get also the current. But very important that at this time should meet, let me say, also the capacitance. Let me show you. Nice, no? Try to think why the capacitance is a little bit more noised. Try to think at all. Try to also at home to tune a little bit better to reduce this time. I would like to show you, I hope, how clever is the Kalman filter. If I put something not realistic. Remember, I already did this example. Let me put a resistance negative. That physically does sense. You remember, in extended Kalman filter, no guarantees for the optimality. I show you this again in the future. No guarantee for the convergence, because it's an approximation of the problem. Something like we realize a convexifization of a problem, which is not convex. But if not convex, could also diverge. Putting something not physical. We say to the Kalman filter, please pay attention. R is negative, no sense. I show you what happens. I can improve. I told you also in the case of the motor, putting the initial value of the P matrix not 0, because now the initial value is 0. Do you remember? If you put the initial value of P matrix, a posteriori error, covariance, and so on, the error, Kalman filter understands that we are the goal. This means we can see that it's lazy here. It's lazy. We need 10 seconds. Because we inform to the Kalman filter with the wrong information. We say, you don't have to do anything. Because we have error 0. We are the goal. Then Kalman filter is so clever by understanding that we try. If you look, I put here, I remember well, P equals 0 in all elements of the matrix. In the current and velocity, it's okay, because we started with current 0, initial value, and voltage 0. This means no energy in the system. But for R and C, it's totally wrong. at the beginning is clear in its time. Of course, in its time also for velocity, for voltage and the current, because everything is connected. It's connected because the system is observable. This means the error is also in the current. You remember your question, Tamo, why the current needs so much time? Which time? Because everything is connected. Could be that the error in the voltage is not so lazy, let me say, because we measure this. I show you now. Try at all to increase P0. How much? PSO. It's in the project. It's in the bachelor thesis. Because the problem of the Kalman filter is to tune. Also in linear case, I told you, also in linear case, because no God knows how the error is. Look at the voltage. The voltage should be a little bit better, or much better than the current. Let me show you together. Why that? Because we measure exactly the state which we want to estimate. This means we are close. I don't want to say to the truth, but I can use this sentence. Did you check the voltage? Is better, no? The reason is what I try to explain now. Let me come back. Where is the voltage? It's not there.
Well, yes, you would.
Yeah, right. Look, almost perfect. I would like to say perfect. Yeah, almost I would like always say because, yeah, just a little bit at the beginning, but it could be a numerical. Yeah. Let me put, and then I introduce the lecture next time. Let me put R negative. Yeah. Yeah, I'm finishing. I'm finishing.
But I have
2 minutes. Yeah.
so this code we can use with our own system, which we find out for the project, right?
Of course, all material which we have in my study can be used for the project, but we have to discuss with which is kind of project. For instance, in your case, you can reconsider in your old paper to do another paper. You can consider a technical drones, everything which you want. We can start, if you decide to work with us with drones, you can start directly here with the bachelor thesis. It's free, very important Kalman filter. If you want, we can do also in a different Kalman filter, which I presented, I don't know, not Gaussian Kalman filter. We read in the literature, you can do whatever you want. Very important, the keyword Kalman filter should be done. Let me use these 2 minutes to show you a negative R. Could also not work with a negative R. Let me show you. Because we put something not physical. Look. Here again, try to put, look, very important, a value not zero here. Look here, no? And a value not zero here to inform that the Kalman filter, that the value R and C is totally wrong. Because with this value here, this and this is correct, okay. Because we are exactly on the initial value. Now we know, but really we don't know how energy is in the system, how much. But here it's totally wrong because we say to the Kalman filter, please, you don't have to go at the beginning, you don't have to do anything at the beginning because we are at the goal. Because he is clever and say, if I have the goal, I don't want to destroy what I have. Because if really we are the goal and I put a big value, it is nervous. It's look for something which is not there, an error which is not there. If I put something not zero and we are on the goal. Look, if I put -5, physically no meaning, no? Could work, could not work. But it could be that Kalman is so clever. In particular, please pay attention to what I say now. If here is 0 and 0, it's extremely difficult to show. Let me see. Resistance, where is the resistance? But it doesn't matter what, probably is here. Yeah. Could work or not work. is not working. Yeah. Of course, but this is something physical stupid. It could work nevertheless. If I put larger than 0, could work. Next time, we will see how many parameters I can estimate in general. For instance, if I put here 100, say you have a big error. Let me see. And next time we will discuss the observability. How many parameters I can estimate using one input measurement, one output measurement. Look at this. No, we are not able to do. It could be, because as I told you, there's physically no many, but it could happen that is work. Of course, I don't want to put a negative resistance because no sense. In order to understand that the Kalman filter, depending on the initial condition, in case of extended Kalman filter, because it's a convexitization of a problem which is not convex. Okay, thank you for your attention. Next week, we go ahead with the observability in this context here. How many parameters can I estimate? Thank you. Ciao. Thank you. Let me close the lecture here with Zoom. Where is now? And then we can open the discussion